Hello, my name is Kwesi Rutledge, and today I will be presenting our work at the Ozay Group entitled Correct by Construction, Exploration, and Exploitation for Unknown Linear Systems using Bilinear Optimization. This synthesis problem was motivated by one of my recent life events. I moved across Ann Arbor. While doing so, I had a friend helping me move boxes to the new apartment. And despite whether or not that person was holding liquids, clothing, or books, they were able to safely carry my belongings into the new apartment. Moving an unspecified load into a new area might be straightforward for humans, but for many robotic or other systems, it is not. Why? It is difficult to handle this task because, first, the box's physical parameters are uncertain, or we don't know exactly what's in it. Second, you must use inputs or your own forces to identify these unknown parameters. You cannot simply look through the cardboard to determine what's in it. Thirdly, you have to move the boxes safely. As is shown on the slide, falling boxes can be quite scary and delicate, as this video shows. Also, finally, there is typically a deadline with which you must move the box. For example, I cannot wait multiple hours for my friend to move a box from the car to the new apartment, otherwise this move will take very, very long. I argue that these characteristics exist not only in the box mover problem, but across a wide range of important control theory problems. And I will look into how problems with these characteristics have been addressed in the past by considering exploration and exploitation trade-offs. By trading off between parameter learning and robust control principles, we can create controllers that solve this class of problems. The area of adaptive control offers some direction on how to do this trading off. For example, adaptive controllers based on barrier functions are able to achieve zero tracking error when robust controllers cannot, as shown in the upper right-hand figure. In terms of the mover problem, being adaptive is equivalent to finding a controller that both identifies the object inside while also making progress towards the goal. In many cases, the exact mass and moment of inertia might not be necessary to achieve the task, and this is something that adaptive control is good at recognizing. Unfortunately, adaptive controllers are frequently much more complicated to design, and little work has been done to make it easy to incorporate complicated finite time horizon specifications into their design process. Now, we are interested in specifically addressing these 2 points by proposing a simple design approach for satisfying complicated specifications like the one we stated for the mover problem. To do this, we will tackle this formal problem statement. Assume that you are given a linear discrete time system, but you do not know the parameters A, B, and the set W from which the noise is generated. You do know that these 3 unknown parameters are a tuple, and that tuple belongs to a known set. You're given the initial state that the system begins the task from, along with the deadline for the task, and the target set that you need to reach by that deadline. The goal is to find a controller such that no matter which model, that is which tuple, is active, the state of the system is guaranteed to reach the target set. Furthermore, I add the following assumptions. First, the target set and all noise sets, W, are polytopes. And second, that there are a finite number of modes or a finite number of tuples to consider. Let's take a look at an example of such a problem. We will consider the drone mover system, which is defined as follows. The state is the position and velocity of a drone in the altitude direction. The control input is a thrust force in the altitude direction, and the noise to the system is a small deviation in that thrust. The unknown model parameter is the mass of the drone. Think of this as the weight of the package that the drone is carrying. The system starts with 0 velocity at a height of 1 meter above the ground, and its goal is to steer this drone and its package to a height somewhere between 2 and 3 meters. With this problem in the mind, let's consider the approach developed in this paper. It can be considered as this pipeline. The output of this pipeline is an adaptive controller which solves the problem. The first component of any adaptive controller is the element that estimates the unknown parameters. We'll begin here. The consistency estimator receives as input the currently observed data, that's the previous states and inputs, and produces all of the modes that could have produced that data. Visually, this is shown on the right in the following way. The blue data point, which is in the cyan region, is only consistent with the cyan mode, or the cyan mass. The magenta data point is in the magenta region, and thus is only consistent with the magenta mode, or the magenta mass. And the final data point is in both regions, and is thus consistent with both the cyan and magenta modes. The estimator produces sequences of these judgments, as is shown in the following examples. We will call sets of these bold M's exploitation profiles. Now, the properties of this estimator will be used to make a guarantee about what values it can create. Specifically, we know that for the drone problem, the estimator outputs one of 3 possible elements at each time, indicating that the sequence bold M can take one of a bounded number of values as a sequence. So, although there may be an infinite number of possible trajectories that the controller can see, there's only a finite number of these bold M's that it must be robust to. This is helpful because while the true mass on the drone is what we want to know, it is not available at all points in time. On the other hand, this estimate, bold M, is something that is always computable online, and thus we can incorporate it into an adaptive controller. Each of the bands in this figure on the right can be thought of as trajectories that all produce the same bold M. We formalize this idea with the consistency set. For example, in the figure on the right, the set of green trajectories would correspond to perhaps all trajectories that produce the estimate green M, which is shown on this slide. Importantly, a consistency set may be empty. This indicates that there are no trajectories that can produce the estimate that you're interested in. What will be useful in our approach will be the set of M's such that the consistency sets contain trajectories. We will call this collection of M's M star. Identifying M star is somewhat time intensive due to the fact that consistency sets are non-convex objects, but we show in the paper how a related convex set R can be used to determine the consistency set properties. With the consistency set in mind, we can now consider what happens when we use a specific controller structure with our estimator. Consider the following disturbance feedback control law. Importantly, it amounts to a linear combination of the data, that is the previous states and inputs, at each point in time. If we assume that this specific controller is used, then we can introduce the idea of the closed loop consistency set, which is the consistency set with the added affine constraint that the input at time t is chosen as a linear combination of the previous data. So, although the consistency set for a given mode may not be completely within the target set, it might be the case that we can find the right controller, aka the right restriction, which does, as is shown in the figure on the right. In parallel to the last section, this object can be represented with combinations of a closed-loop reachable behavior set, R, as well. We can incorporate the closed-loop consistency set into an optimization problem that solves our task. But to do this, we need to add some extra constraints. The adaptive controller can be thought of as a collection of these disturbance controllers, one for each bold M inside of the profile M star. And the constraints we need to add onto this collection are first, that the controller gains for each sequence bold M bend that sequence's closed loop consistency set into the target set xt. Because the closed loop R set is a polytope, this amounts to a polytope in polytope containment problem. Unfortunately, because of the structure of R, this results in a bilinear constraint in our final optimization problem. The second constraint on the adaptive controller relates to how we select the right controller at a given time. Remember that we don't know the true mode, or even the full sequence bold M a priori. So how does our adaptive controller pick a controller from this collection that it has? We add the following constraint. If the prefix of two estimates, bold M and bold M prime, are the same, and that the x's and u's are the same, then the output of both controllers should be the same. This can be written as a linear constraint in our work. And what this does is, it makes it so that if the adaptive controller chooses any bold M with the right prefix, that the output will always be the same. So, in summary, the first part of this pipeline defines the set of all feasible estimator outputs and is quite computationally complex. It creates the profile M star. The second half of this pipeline identifies a collection of controllers for each sequence M in the profile M star. It formulates a bilinear optimization problem that steers every bold M's closed loop consistency set into the target set. We use this approach in the following opposing rotation system. This system contains two nearly identical linear systems, but the A matrix is different between the two modes. One A matrix is the rotation matrix for positive pi over 4 radians, and the other A matrix is the rotation matrix for negative pi over 4 radians. Critically, this system does not exhibit a robust control solution, but we can see that by using zero input, we get something that is very close to a solution. Our pipeline finds a solution for this problem with an M star that contains only two values, and this means that the algorithm correctly identifies which way the system is rotating at time t equals 2 and then solves the problem. Secondly, we revisit the problem from earlier, the drone mover problem. Again, this method is able to solve the reachability problem regardless of what the mass is by falling at first while identifying the true mass of the drone before then rising to the target location approximately 2 meters above the ground. Now let us revisit the pipeline that we mentioned earlier. Note that this first part was used primarily to detect which bold M's had a non-empty consistency set. While this is done in a separate step here, we know that by using the Farkas lemma, we can actually include constraints on emptiness and non-emptiness inside of an optimization problem. So we can create a new pipeline where instead of generating M star, we can pick whatever M we want, and we can enforce non-emptiness or emptiness using the bilinear constraints of the Farkas lemma. How the designer chooses M has some interesting interpretations. But we will present some intuition of those interpretations here. First, one can provide an M like the one on the left side of this screen for systems with two modes. What this M defines is that we want to find an adaptive controller that will learn the true mode of the system by the deadline of step t equals 2, or this point in the time horizon. On the other hand, there are M's like the one on the right side of the screen, where the controller takes actions that are meant to hide the true mode of the system for all time. Thus, we have a method for defining epistemic or learning-based constraints on the desired behaviors of the system. In summary, the work presented today first provided a framework or pipeline which can be used to identify adaptive controllers for unknown linear systems that satisfy reachability specifications. Then we modified that framework so that we could encode arbitrary epistemic constraints into the desired controller. And then finally, we applied this approach on several examples in the paper. In the future, we would like to extend this work to nonlinear systems and systems with compact sets of unknown parameters. Thank you.